I like to present lecture 2 of this lecture series, and title of this is Asymptotic Analysis Method. This is the one circuit analysis technique or system analysis technique. We will be applying this technique to analyze the voltage mode controlled buck converter, small signal design, control design, and the evaluation of closed performance. Okay, so I'd like to introduce some details about this asymptotic analysis method. Okay, you know this man, David Middlebrook. He was professor in Caltech, USA, CIT. Okay, I think he's the most famous people in power electronics society so far. I think he's the father of power electronics, and he developed this type of analysis, design-oriented analysis. Okay, so you will be knowing this details about this. Okay, and this asymptotic analysis method is the most essential part of this. He proposed, Dr. Middlebrook proposed this design-oriented analysis, and this is the obligation of design-oriented analysis. This is rather well-known terminology, and he proposed and promoted and advocated, but unfortunately he died maybe 5 or 10 years ago. So this topic is not published in the textbook format, and he made some monograph, lecture material, and he provided many seminars, symposiums, tutorial on this. Okay, so the key element of this design-oriented analysis is asymptotic analysis method we'll be using in this lecture series. Okay, design-oriented analysis means the analysis, circuit analysis, is usually. Okay, you can derive something very long expression, but it does not provide any insight about the circuit behavior, or it does not provide any useful information for the design of the circuit. Okay, that is the conventional method. But this design-oriented analysis is aimed to provide design insight of circuit or system. Okay, so this is a graphical method, and we are using the Bode Plot technique, especially this asymptotic plot technique. Okay, you will understand the details about this. Okay, and there are many applications. This is the very general methodology, so it can be applied to any systems, but particularly we will be using this to PWM converter, closed loop controlled PWM converter. We will be using this to derive a transfer function of something. Okay, actually we want to replace this transfer function manipulations with this approach, graphical approach. We avoid any tedious calculation, and graphically, and we will have the insight to transfer functions of something very complicated system. Okay, and we will be using that technique, the control design, namely the feedback compensation design, and we will use that technique, performance analysis in frequency domain and also in time domain. Okay, so, and finally the feedback design optimization can be achieved using this technique. Okay, asymptotic analysis method. There are many potentials of this method. Okay, another example is maybe the later part of this lecture series, maybe next semester, we will be dealing with DC power distribution system, where many PWM converters are connected in series, in parallel, and or a combination of them. So very complicated system. So for the system level analysis, we will be using this asymptotic analysis method to evaluate the stability of the system. Suppose you have two systems, two converters. This one is stable, this one is stable. So they are individually stable, but if you connect them together through some filter stage, but system can be easily unstable. Okay, something like that. In the system, evaluating the system stability is very different from the evaluating the stability of individual subsystems. This complicated DC power distribution system requires some techniques, okay, and we will be using this asymptotic analysis method along with the other techniques. There are just some advanced circuit theorem, EET, extra element theorem, and the feedback theorem, and many others will be used for this. Okay. Another topic is system comparability, subsystem comparability. If you have one system, one converter, and they are good individually, stable, and it has high performance, and you connect them together, they interact dynamically. This performance of each individual converter will be affected by the presence of the other one, each other. That is called subsystem interaction, dynamic interaction between subsystems. And comparability means if two subsystems are comparable, there is no interference degrading the performance of the system or individual subsystem. That is the problem of subsystem comparability, subsystem interaction, and subsystem stability. Okay. And another technique based on this with other techniques is you can program the performance of the entire system and the individual system. You can program. You have some desired performance of your system. Of course, system should be stable. Then you can program that with some design. Okay. Programming feature will be embedded in the design process. That is possible using this asymptotic analysis method and something else. Okay. So in this lecture series, our interest is about this application to control design, dynamic analysis of buck converter with voltage mode control will be analyzed or implemented using this asymptotic analysis method. Okay, so this section, this lecture, introduce the fundamental basics of this asymptotic analysis method, which is very important. The fundamentals of the entire lecture series. Okay, so you need some information about this small signal model of closed loop controlled PWM converter. So this is the voltage mode controlled buck converter. This is a small signal model of power stage, and this is a small signal model of modulator, and this is a small signal model of voltage feedback circuit. So compare this with, try to compare with this, okay? Originally the circuit, this is the circuit diagram, small signal circuit diagram, okay? So it was presented in this page, and later on we will be using this block diagram representation. So you know the equivalence between them. So they are same, but we are using some different representation here. So this is they call it circuit model, small signal circuit model of buck converter with current mode control. Okay, first one is loop gain is important because loop gain determines the stability of the system. So loop gain is defined as negative gain product of functional transfer function, product of gain term presenting in the feedback path. Okay. So first, this is the duty ratio, and output variable is here. So transfer function from here to there is this one, D hat input and VO hat output, and this VO hat output voltage is sensed this voltage feedback circuit, and it converted this control voltage. Okay, so transfer function from here to there is this one, voltage feedback compensation. Okay, and we have minus sign here in between because voltage feedback compensation circuit. Oh, okay. This one is okay. This one is okay. And this is control voltage. This is the duty ratio modulation. Change in duty ratio. There is another transfer function. Okay. Some student cancel this, cancel this, cancel this, cancel this, and this becomes the -1. Okay. That is the stupid story. Okay. The meaning of this is multiplication of 3 different transfer functions. Okay. So this one is GVDS. This one is FVS. This one is FM. Okay. So this one is we named this as GVDS. Right. And audio susceptibility, or this we call it input. Okay. Actually the disturbance, AC disturbance in input source. So when we are talking about this, we are talking about the sinusoidal component of the AC. Okay. Input voltage, and actually this is the 0, and this height is DC value of this input voltage, and this sinusoidal component is Vs hat. Right? So we are only talking about this Vs hat. Okay? And this is the input, and this is the AC component contained in the our voltage. So assume this is some noise. So noise is coming from the input voltage. Ideally, input voltage is constant voltage as a battery, but in practically, this our voltage is derived from AC voltage with some rectification circuit. Okay, probably most DC voltage is there is AC voltage, AC grid, and you have rectifier in between, and this is rectified voltage has some this kind of sinusoidal noise component. Okay. So this specifies this noise voltage is how much attenuated here, okay, or how this input noise is transmitted to the out voltage. So it is, in terms of its functionality, it is better to call input to output noise transmission, right? But we call it not the older people's. Okay, some people call it audio susceptibility. Okay, so very strange term, right? In the past, the switching frequency of this DC-DC converter is in the range of audible frequency range. You know what audible frequency is? Okay, the lowest frequency one human can hear is maybe 20 hertz, and the maximum frequency, the highest frequency the human can hear is 20 kilohertz. So audible frequency is any signal in the range of 20 hertz to 20 kilohertz. Okay. In the past, the switching frequency of this converter falls in the audible frequency range, maybe 1 kilohertz. Okay. So in this converter, there are many magnetic components. Okay, inductor is a magnetic component, transformer is a magnetic component, and the magnetic component is excited at that switching frequency, turned on, turned off. Periodically, it generates some noise one man can hear, like zzz. There, okay. So in the past, all the power supply is generating that kind of noise. So at that time, the noise in this DC converter is in the range of audible frequency, so they can hear it. Okay, so the noise is generated here, then noise will be transferred to here. So if noise is transmitted without small attenuation, then this converter is very susceptible to the noise. Okay, susceptible means one is susceptible to something else. One can be easily affected from bad things. Okay, this means how the noise is attenuated or transmitted, transferred to the output is called audio susceptibility. Okay, so it's the same thing, input to output noise transmission. So many people call it audio susceptibility. Okay, and this one is our voltage as a transfer function from here to there. Okay, so if there is some noise, okay, noise is coming in the output current, or some distance is changing, or this noise current is modulated from fixed value in the sinusoidal fashion, then output will contain the sinusoidal component at the same frequency. Okay, characteristic of that is called output impedance. So you are using output impedance in many times in audio amplifier or any amplifier. This is a very important parameter. Okay, so for the ideal voltage source, so when you are making or designing this converter, you want your converter to behave as the ideal voltage source. What is the ideal voltage source? The voltage here is constant at DC. Whatever is coming in, the input, and output is constant. Whatever is coming in the load current, some step change or some sinusoidal noise, okay? So it should remain constant absolutely. That means this should be zero. This should be zero, okay? So ideally, for the ideal voltage source, audio susceptibility is zero, output impedance is zero, then output voltage becomes constant. Whatever happens in the input port and output, okay, that is the desired characteristic of ideal transformer. Of course, it is impossible to achieve this. So then what you can do? You try to minimize this for all the frequencies, right? That is the one of your design goal. And another one is, of course, converter should be stable. Stability is determined by this transfer function. And this one, they determine the goodness of your converter as an ideal voltage source. Okay? So you should achieve this stability while minimizing this altogether. That's your target of design. Okay? Okay, so let me switch the block diagram representation of this converter model. So this one and this one is the same thing. Okay, so loop gain is defined as here. So gain product of this, and the minus sign in front of it. Okay, that means you have negative sign in front of this, and this one is this, and this one is this. Okay, you have additional negative sign here. So there is initially minus sign, one minus sign here, and here another negative sign. They cancel. Okay, one is here, another one is here. So loop gain is simply multiplication of three transfer function blocks. This is a Dewey ratio to output transfer function. This is a voltage feedback compensation. This is a modulator. Okay, this one is fixed, right? Power stage circuits are fixed. This is fixed. If this ramp height is fixed, FM is fixed. To modify this TMS, there is only one option, one available variable you can change. That is this one. Okay, so you will be designing this to achieve the stability and good closed loop performance. Right. So this is loop gain, very important. And audio susceptibility is transfer function from here to there. So this one, and this is the open circuit input to output transfer function, and 1 plus loop gain is shown here, and output impedance. This one is open loop input load current to output transfer function, and 1 plus Tm appears here. Okay, so this is open loop, and this is closed loop, and this is the closed loop. Right? Okay. You can derive this using the Bayes gain rule. You learn from the cultural course or block diagram representation. This is very easy, trivial to derive this. Okay, so we assume this is correct. Okay, I assume you know this, right? All right. So asymptotic analysis method. Asymptotic analysis method. The purpose of this is for construction of asymptotic Bode plot of transfer functions okay. We'll understand this later. Okay. Suppose, okay, this is our block diagram of our column mode controlled for converter. So you have block diagram and the loop gain expression. We already know the expression of the loop gain, which is a product of 3 elements without minus sign because there is additional minus sign, so they cancel. And this audio susceptibility is given by this, and output impedance is given by this. We went through this, okay. Then we use this approximation. It's not an approximation, okay. This sign means approximation. In exact sense, we don't use this. We use this sign. This sign is they are same by definition, okay. So I'm not talking about the approximation. Of course, approximation is also true, but we are using this. We define this. So the content of this is, so we have this in the numerator, we have this in denominator. If magnitude of TMS, this one, is larger than 1, we ignore this, okay? If TMS is much larger than 1, that is obvious to ignore this, okay? But here we are ignoring this as long as this one is larger than this, okay? Slightly larger than this is okay, all right? If they are not the same, then we use this and we consider for this range, this frequency range, this one is expressed like this, we drop this, okay? And this one is after some frequency, TMS is smaller than this, not much smaller than it, just smaller than this one. Then we ignore this, then it becomes GBS, right? So this is another approximation. This is a new definition for the asymptotic analysis. You can consider this is the approximation, but that is not correct. In exact sense, this is a definition, okay? Same is true here. So we'll use this kind of definition here, okay? So this is the basic idea about this asymptotic analysis. Actually, this one is not new. We are using this in other places. When plotting the Bode plot, we ignore something like that. But we are not ignoring anything. You are defining this one, newly defining this one. Okay, so why this is useful? This is the typical shape of loop gain magnitude. Okay, so at low frequencies, magnitude of a loop gain is very large. It decreases monotonically, it decreases gradually, and it passes this 0 dB line. This 0 dB crossing frequency, we denote it as omega c. Then after this frequency, it keep on decreasing like this. Okay, this is the general shape of loop gain. Okay, so for this frequency below this frequency, we consider this is this one. Okay, after this frequency, we take this. Right? without any approximation. This is definition. There is a concept of approximation involved in here, but assume this is a definition. Okay? And so this is the natural borderline for these two different expressions. For the closed loop transfer function, there is the loop gain crossover frequency here. Okay? So there is only one borderline. Suppose, so this is very good. Actually, all the loop gain of the converter looks like this. Okay? Suppose converter, some strange things, loop gain is something like this. Okay? Then this technique is use this, right? So there are three borderline here, here, here. So it makes this problem more complicated than before. Okay? So we are not considering this case. We are only considering there is only one borderline in here, and that is the loop gain of this system. So this approach is called asymptotic analysis in the simplest possible form. There are many other forms, something similar to this. This is the most simple one, simplest example of this. Okay, so I'd like to discuss three example cases. First one is this. Suppose there is a relationship between GS, TS, and FS. This relationship, this is very similar to this one. Okay, so I intentionally select this because the final application of this approach is 2 there, right? So now assume this is the constant, which is smaller than 1, and this loop gain is this one. This one is what? Omega C divided by S is integrator. And first, consider this exact expression. Exact expression is GS is coming here, and the TS is coming here. Okay, this is the exact expression, and you multiply omega C here and S here, and you modify this, rearrange this equation, then you will have this. Okay, so this is the exact expression. So this is the exact things. All right. Somehow we want to use the previous asymptotic analysis method. So we take this. Okay, it's not approximation. It is definition. All right. So for this frequency range, we use this, and for this frequency range, we use this. And this is the Bode plot of this. This is the integration. So at low frequencies, magnitude is very large. Okay. At this frequency, S equals omega C, it becomes 1. Then there is a 0 in dB scale. So omega C is here, and it's declining like this. And the slope is -1. There is -20 dB per decade. Okay. So this is the Bode plot of this one. You sketch Bode plot of this. Okay. Then you sketch Bode plot of this. This is constant, and value is smaller than 1. So it is negative something. 0 dB line is here, and the negative something is here. Okay. So you have two curves, this one and this one. And forget about this part. And from graphically apply this. After loop gain crossover frequency, it follows the asymptotic plot of GS, which is this. Okay. Below this frequency, it follows this one. This one is GS divided by TS in dB scale. In log scale, this is what? GS in dB minus TS in dB. Okay, subtraction, right? So at this frequency, there is nothing to subtract because 0 dB. And at this frequency, you are subtracting this much from here, okay? And here, you are subtracting this much from here. Then you have this increased slope, okay? So this slope is +1 because this horizontal line slope is 0, and you are subtracting from 0 to -1. Okay, slope here is -1. then slope becomes what? 1, okay? Which is 20 dB per decade. So graphically, this is same as this, okay? You convert this into transfer function expression, right? So consider low frequency part first. So here you have, this is a differentiation, right? So here is S, and you have some gain, okay, unknown gain, KF. But you know this, you extend this line segment, then it passes, it crosses this 0 dB line at this frequency, 1 over KF. Because if you put 1 over KF here, it becomes 1, which is 0 dB, right? So this part is, this graphical part is converted into this equation part. And this part is, there is what, this is what? This is the pole, right? Pole is located at this frequency. So 1 divided by 1 plus S divided by omega. This is the pole, okay? So this is a multiplication of this part and this part. So this part is coming from this part is coming from this, and this part is coming from this, and this is coming from this, okay? Then you have expression here. Then you need to find out this KF, okay? To evaluate KF, consider this frequency, omega C. At this frequency, then at this frequency, this line segment is valid because this is the line segment passing through this. At this frequency, you put this omega C here, that value is what? Kg, okay? That is the what this plot is saying. Then this evaluate this magnitude, evaluate at this frequency is this one, okay? This one is Kg. That means this is this Kf times omega C is Kg, okay? This is from this graphics, okay? Of course, you can obtain this from the calculation, but we are only using these graphical things. Then from here, you find out Kf as this one, then put Kf here, then which is the same as this, okay? So this is the exact circuit analysis, or this transfer function manipulation, and this is asymptotic analysis, has the exactly same result, okay? You may think this is the more complicated than this one, but this is a very simple example, okay? For the other examples, you cannot do this, so complicated, okay? But you always do this graphical analysis using this approach, okay? So in here, the exact analysis and asymptotic analysis are the same. So let me give you another example. So you have same form, but GS is this one. And again, this TS is this one. Then this is the direct evaluation of this transfer function. And you have this, okay? Here you take the graphical approach. So you have two different asymptotic plot. So G is this one. So it starts 20 log Kg, and you have pole at omega P. Then slope becomes 0 to minus 1. All right, you have one here. You have another one, which is integrator. Integrator is passing this point here. So you have this one and this one. So with these two line segments, you obtain the resulting asymptotic plot of this transfer function. Okay, so rule was after this frequency, you follow this one. Okay, this is G. So G part is coming here. G part is coming here. Okay, and below this, there is a subtraction. So you are subtracting this from this. Okay, then there is nothing to subtract. Okay, then this one, this length is the same. This length and this length is the same. Okay, because you are subtracting this much from this one, subtracting from 0 line, same length. Then you have this, and this is the same. Length of this are the same, and the length of this are the same. Okay, that is the way of drawing this asymptotic plot, or you can use the slope information. Okay, slope here is -1, slope here is -1. So in this part, -1 minus -1 is 0. 0 means horizontal line, and in this part, slope here is 0, right? 0 minus -1 is +1, so slope is increasing. Okay, so this is one way. Another way is you just subtract these things. Okay, so length of this is length of this, length of this, and so on. Okay, so this is the result of the asymptotic analysis, and you convert this into this equation form. Again, you have differentiation, this part, and you have this is increasing, so it is decreased by 1. So you have one pole here up to here, and you have another pole here. Okay, so assume this is KFS. Use notation of KFS, and you have a pole here. This omega p is coming here. Another pole at omega c. This is expression, and you need to find out this KF. Okay, to evaluate KF, you just take a look at this part. This part. Okay, so just use this and this transfer function evaluate at this frequency. At this frequency is subtraction between this. This is what? This is kg. 20 over kg is here, and subtraction of this much, okay, this much, all right. So this is equation of this is S divided by omega c, and you are evaluating omega c divided by S, and you are evaluating that frequency at this point, omega p point. So we are subtracting this length, then we have this linear equation, kg minus is division, then kf is given by this, which is same as this one. Okay, so you understand this. Okay, this is a way of constructing this. You need some practice here. Okay, but this one is easy. Later on, it becomes almost automatic procedure. Plotting this. Okay, so you have another example. Okay, here this exact expression is the same as asymptotic expression, but these two are special example. The simplicity of this TS provide this result. In general, there is just some deviation. Okay, so this third example, we see the difference between two expressions. Okay, now this is the kg, and this is this one, something complicated. So exact expression is kg divided by this one, and rearranged into this form, right? And how about this asymptotic analysis? Just first plot this one and this one individually. Okay, let's consider this first. So initially it has integration. So there is integration, and this line segment is looking at this omega c, because at this frequency omega c is here, then this one becomes 1, which is 0 dB, right? So it was declining, looking at this point, but in the middle there is a 1 0 here. So 0 is reducing one pole comes first. So pole is increasing this slope from -1 to -1 to -2, and at this frequency there is a 0. Then slope is changed, increased by 1. So -1, -2, -1, and this is 0 dB crossover frequency omega c prime, which is different omega c, different from omega c. Okay, so this is our T plot, and this is constant, which is smaller than unity. So there is something in negative dB here. Okay. So this is the G, right? And follow the rule of asymptotic analysis. After this, take this one, and before this, you subtract this from here. Okay, that is the definition of this asymptotic method. So at this point, there is 0, so there is nothing to subtract, and here the length of this becomes the same, and at here length of this and this becomes the same, and at this point this length and this length should be the same. Okay, this is the asymptotic approach, right? So from this you write down equation. So initially you have differentiation, so KFS, and at this point you have 0. Okay, so 0 is coming here, omega p, so it's increased, and here is one pole at omega g, another pole omega c prime. Okay, final task is to evaluate this one. Then you take a look at this part. This part, okay. So this line segment evaluate at this point is KF S evaluate at omega p. This is the omega p frequency. It's the same as 20 log kg minus this one. This length, we know this, right? Because this is S divided by omega c. This part, no, omega c divided by S, and you evaluate this one at this frequency. So this length is omega c divided by omega p. Okay, so this part is this part. From this you evaluate this. This is the KF. Okay, so when you are comparing this part, they are the same, and this part is also same, but this denominator is different. Okay, so this is factorized. So this is not factorized. It is impossible to factorize this in this form. So there is some difference. So you may want to check what is the difference, how much that difference affect the final result of your analysis. For this case, the exact solution is different from the asymptotic analysis solution, and the difference between them is negligible. Okay, I have two plots here, and this is the example. So I took this example. GS is this one, TS is this one, and I plot the result of exact analysis and result of asymptotic analysis. One is asymptotic approximation, another one is exact equation. It's not approximation or asymptotic method. Then this magnitude curve is almost same, and phase curve there is a small deviation, extremely small deviation here. Magnitude the same, almost same, so can be ignored, right? So this approach can be taken regardless of complexity of this and this. Okay, that is the best feature of this approach. Okay, in this approach, you don't have to any calculation, just to watch the asymptotic plot of individual transfer function and construct the asymptotic plot of composite transfer function, and then from the asymptotic plot of composite transfer function, write down the equation, resulting equation immediately, and you find out the unknown coefficient very easily. Okay, so that is the idea of this asymptotic analysis. Okay, maybe you are not familiar with this approach now. You don't have to worry about much. Later on, you will learn this. It becomes almost automatic after some practice. Okay? Right. I wrote down some procedure here. So I don't want to go through this line by line. So this is the procedure. I took this page from my book, okay? So I already explained this, the procedure of FS sketch, asymptotic plot of composite transfer function, and the only important one is sketch this GT individually and sketch F from the high frequency, okay? Suppose this is the frequency, then this is log scale, this is linear scale, you have scale, then you go this direction, okay? From the other way around, from high frequency to low frequency, you move in this direction, okay? And if you finish the sketching the asymptotic plot of this function, then you should convert that into the transfer function, and this is the rule. And two important rule is express them in time constant form. For example, like this, okay? 1 plus s divided by something, not s plus something, okay? This is the frequency, this first form. So use this form, right? So, and do this from the low frequency. The way of going is now you start out from this low frequency and move to the higher frequency, okay? And some details are also written down here. You don't have to read this now. Later on, after finishing 2 more lectures, something like that, then go back and read this, okay? Then everything will be clear, okay? Use of this is obvious, okay? Use of this is obvious because this is our small signal block diagram model, and in model you have this is a typical shape, okay? Then always this type of expression appears during the analysis or construction of something, or this compensation design. Then use this approximation, this new definition. All right. So then you perform this. Okay. So this is the basic things, fundamentals, concept, or some examples of asymptotic analysis method. I think you are using this approach in the past, okay, without knowing this, right? So this time we formalize this, we give the name as the asymptotic analysis, and we try to apply this procedure for the arbitrarily, maybe complicated systems, okay, without any hesitation. That is the purpose of this, okay? All right. So this is the end of these things.